Hello guys, welcome to day 5. I'm just going to come at you today with hopefully a shorter note, just looking at evaluating limits at infinity algebraically and some concepts we can get here to help us solve these. Not sure what that update is, but we'll continue on. So when we look at especially rational functions, it's important to understand what's like how powerful the top or the bottom is. So when we see something that is more powerful over less powerful, again, these are limits as x goes to infinity. When we see something more powerful over less powerful, our limit is going to be either positive or negative infinity. Because again, when we're dividing two big numbers, if the top is much more big than the bottom, we're going to end up with a big number, either a big positive number, infinity, or a big negative number, negative infinity. When we see the reverse, right, something less powerful divided by something more powerful, we're going to get 0. Again, think you're dividing two big numbers, but the bottom is a lot bigger than the top, right? Like 1,000,000 divided by 1,000,000,000 is a number that's very close to 0. Okay, and as x continues to get bigger and bigger and bigger, that more powerful denominator is going to drive that function closer and closer and closer to 0. Okay. What's most interesting is when we have equal power. Okay, when we have equal power, we're going to look at the ratio of the coefficients. Okay, so let's talk about what makes something powerful or not powerful. We're going to have kind of a hierarchy of powers. Our highest powered functions are exponential functions. So things like e to the x, or like that's just a base of e, could be a base of any number as long as it's bigger than 1. So like 2 to the x, 5 to the x, 10 to the x. These are our most powerful, and they're even more powerful than really high polynomials. Okay, so those are our highest power, right? Kind of our mid-tier. Would be polynomials. So like x squared, x to the 4th, x to the 11th, right? The bigger the power, the more powerful it is. Even things like, don't forget square root x. The polynomial. And again, square root x just means x to the 1/2. Now obviously x to the 4th is more powerful than x squared. X to the 11th is more powerful than x to the 4th. Okay, but those are kind of our medium power. X to the 11th is not nearly as powerful as e to the x. Okay, especially as x goes to infinity. Okay, then our lowest power are actually the inverse of our high power, and those are logs. So things like natural log x, log of any base x. Okay. Now we're going to get to the more interesting stuff when we end up with same powers being dominant. Okay, but let's just do a couple examples here. Okay, so if we take a look at this example here, we're doing the limit as x goes to infinity of x to the 13th over e to the x. Now, you say x to the 13th, that's pretty big, right? If I plug in a huge number into x to the 13th, if I take a huge number to the 13th power, that's going to make a really, really big number. But so is e to the infinite power. Okay, so we kind of want to look at which one's more powerful here. E to the x is going to always be more powerful than x as a base to a number. So we can know, okay, the bottom is more powerful. When the bottom is more powerful, the limit equals 0. Okay. But I want to talk a little bit about e to the x, these exponential functions, because when we start including negative infinity here, we've got some interesting things happening. So first off, it's very helpful to understand what the graph of e to the x looks like. Okay, e to the x is an exponential function, right? You can always plug in to get some points, right? So we can plug in 0. When I plug in 0 for x, e to the 0, any non-zero number to the 0 power gives us 1. So we know that it has a y-intercept of 1. Right, e to the first would be just e, just like 2.7 something. E squared is going to be a bigger number. E cubed is going to be a bigger number, right? This thing gets really big really fast as x gets more and more positive. But let's think about what happens when x gets more and more negative. Okay, let's just think of e to the negative 1. Let's think about how did we deal with negative exponents? Well, we know that we can move a negative exponent into the denominator to become a positive exponent. So this is, and keep that coefficient of 1 up top. So this is the same as 1 over e. Well, that's like 1 over 2.7, whatever. Right? That's a number less than 1, but greater than 0. And we think as we get bigger and bigger negative numbers, what's going to happen here? Right? Let's think about f of negative 5. Well, again, that's e to the negative 5, which is 1 over e to the 5th. Well, e to the 5th is a really big number. 1 divided by a really big number is a number very close to 0. So this graph, as we go back here, keeps getting closer and closer and closer to 0. Okay. So when we have e to the x, if our x is going to infinity, our function is going to infinity. But if x is going to negative infinity, then our function is actually going to 0. So e to the x can be a little bit of a tricky one. Okay, let's try another example here. We'll come back to that in a second. Okay, so when we see this problem here, we are asking ourselves, okay, I've got a limit as x goes to infinity. Right, plugging it in, I'm going to get a big number on top and a big number on bottom. Okay, but that could mean a lot of different things. We could be going to a number, we could be going to infinity, we could be going to negative infinity, or we could be going to 0. So we want to look at the biggest power. Our biggest power up top is the 4th power. Our biggest power in the denominator is also the 4th power. We see that their powers are the same. Okay, and when we see that powers are the same, they're going to, right, the other things here don't matter. The 5x squared plus 2, the 7x cubed minus 8, those will not be nearly as powerful as the 20x to the 4th and the 4x to the 4th. So in a sense, we can kind of just not look at these. Okay, they're not going to factor in when x gets infinitely big. So here we have 20x to the 4th over 4x to the 4th. Right, 20 times a big number divided by 4 times that exact same number. So it makes sense then that our limit is the ratio of those coefficients. It's 20 over 4, and we're going to get an answer of 5. So let's think about this same problem as the limit as x goes to negative infinity. Okay, of the same function. So we've got 20x to the 4th. Again, think about a negative number being raised, a really big negative number being raised to the 4th power. Again, that's going to make that number a positive, very big number. Same in the bottom. And once again, the other functions, the 5x squared plus 2 and the 7x cubed minus 8, aren't going to factor in. And we're going to get 20 times a huge positive number divided by 4 times a huge positive number, which is just 20 divided by 4, which is going to give us 5. Okay, so when we take a look at this problem, we say, okay, the top is going to get infinitely big, the bottom is going to get infinitely big, but the top here is more powerful because it's got a 5th power versus this 4th power. Even though the denominator is getting big here, the numerator is getting much, much bigger. We just have to check the signs here, right? And an infinitely positive number to the 5th power is going to be positive. Infinity to the 4 is also going to be positive, right? So we're going to get, since it's positive over positive, we're going to get positive infinity. If we think about our end behavior here, as x gets more and more positive, y gets more and more positive. Okay, let's think about the same function as x goes to negative infinity. Again, plugging in an infinitely negative number, the top is still more powerful. So I know my answer is either going to be plus infinity or minus infinity. But we have to think about signs here. A negative number to the 5th power will become negative. Okay, so the top here overall has a sign of negative. But in the bottom, a negative number to the 4th power overall is going to have a positive sign. So I know it's going to infinity, but since the top is negative and the bottom is positive, just looking at those most powerful ones, we see that this is going to go to negative. However, if I just went in and changed this 5 to a 6, then that would change this answer to positive infinity, because the top would be positive and the bottom would be positive. If I kept this as a 5, but changed this 4 to a 3, they would both be negative, and a negative over a negative would make a positive, and we'd get positive infinity out here. Okay. Let's take a look at one more example here. Okay. So here, when we take a look at this one, limit x goes to infinity, right? I think about powers. Well, the biggest power is e to the x in the top. The biggest power in the bottom is also e to the x. So they're the same power. So as x goes to positive infinity, those e to the x's are, in a sense, going to cancel each other out, right? Because they're going to make the same number, however big it is, it's going to be the same on top and the same on bottom. And we're just going to get that ratio of the coefficients of 6 over 2. Something really interesting happens, right? So if we looked at this function, we'd see that this thing has a horizontal asymptote at 3. As x gets more, as we go farther and farther to the right on our graph, this thing is leveling off at a value right around 3. But this gets interesting when we take a look at the limit as x goes to negative. Again, just as a reminder, the limit as x goes to infinity of e to the x, this is why we looked at that graph, is infinity. But what about the limit as x goes to negative infinity of e to the x? Well, again, going back to our e to the x graph, we see as x goes to negative infinity, our function goes to 0. So let's think about this same exact function. And think about as x goes to negative infinity. Well, again, what's happening to that e to the x, right? When I plug in a negative number for that x, e to the negative x, or sorry, e to the negative infinity, that's going to 0, right? So both of these terms are going to 0. And again, it's because of this little negative here. So 6 times 0 is 0. Sorry, 2 times 0 is 0. So what I'm getting here is 0 plus 12 over 0 minus 3. Well, hey, 0 plus 12 is 12. 0 minus 3 is negative 3. 12 divided by negative 3 is negative 4. Okay? So take a look at this graph. I went ahead and typed this in. Looks like I typed in the negative and the positive differently. That's fine. It won't alter the problem. When we take a look at this graph here, yeah, we see exactly what we talked about. As x goes to infinity, our y gets closer and closer to 3. As x goes to negative infinity, our y gets closer and closer to negative 4, which is exactly what we had found algebraically. All right, that's it for today. We're getting ready to start testing soon, so make sure you're caught up on all your notes, and I'll see you guys in class on Thursday. Bye.